Hey everyone, in this lesson we are going to discuss how can you do the load estimation. So in the previous lesson we discussed what is load estimation and why do we need load estimation. Okay, so how can we do load estimation? So first we have to understand that there are four types of loads in our system. First we have the lighting loads, okay, in our system, and we have the power loads or the sockets loads, and we have the HVAC or air conditioning system, and then we have other loads such as elevator or lifts, fire pumps, water pumps, laundry, medical equipment, and so on. Okay, so by using the code we can get the lighting loads easily, power loads, HVAC loads as an estimation. Okay, the other is done usually by mechanical engineers, or you can just use an approximation, which I'm going to show in this lesson. Okay, so first we have to understand that we are going to use the NEC code. So according to the NEC code, we have the place. As you can see here, we have banks, cafeteria, computer center, office, library, restaurants, schools, theaters, and so on. Shops, garages, hospital, hotels, and all of this. Okay, each one of these inside the NEC code or National Electrical Code, you will find that we have lighting, we have small power or the power sockets, okay, and we have AC or the air conditioning system or the HVAC system, depending on the system you are using. Okay, so the units in each of these according to as you can see in the place, for example bank, we have lighting, small power, air conditioning. For lighting, small power and air conditioning, you will find that the unit in volt ampere per meter square, which is volt ampere is of course the unit of the apparent power, or S. Okay, and we have here meter square is the unit of the area. So here the power required is given in the form of volt ampere, 1 volt ampere for each meter square. So as an example for banks, as you can see, it can be from 20 to 40. You can select this as 20 volt ampere per meter square, or 40 volt ampere per meter square, or a value between them. Okay, so the minimum is 20 volt ampere per meter square, maximum is 40 volt ampere per meter square. Same as for the small power or the power sockets, you will find here 30 volt ampere per meter square. For air conditioning, from 50 to 70 volt ampere per meter square. Okay, so you can select any values you would like between this range. Now, what is the recommended values which you can use? If you have a range, then select the average, so that you don't select the highest value or the minimum value. Okay, like this. If we assume bank, we are sizing using in a bank, for example, and we would like to do the load estimation inside a bank, then we will usually take the average of the range. As an example, in the lighting, we have 20 to 40. Okay, so what's the value which we can select volt ampere per meter square? We will select how? By using the average, 20 plus 40 divided by 2. 20 plus 40 divided by 2 gives us 30 volt ampere. 30 volt ampere is between 20 and 40, or the average value. So we are going to select 30 volt ampere per meter square for lighting. Okay. Second, small power, as you can see here for small power or sockets, you can see 30 volt ampere per meter square. For air conditioning or HVAC system, we have 50 to 70 volt ampere per meter square. So we can select the average. 50 plus 70 is 120, divided by 2 is 60. So 60 is the average value here. So we know now that lighting, for each volt ampere per meter square, we know lighting will select 30, for sockets 30, For air conditioning or HVAC, 60. Okay. Now, what is the next step? We selected our building type of place. Then we selected the volt ampere per meter square. Now, what is the next step? We need to convert the volt ampere per meter square into volt ampere. So we have to multiply this summation 30 plus 30, which is let's type this. So we have total volt ampere is equal to total per meter square, of course, is 30. Okay, 30 plus another 30 for sockets 30 plus 60 for HVAC, 60 like this, or air conditioning, equal to 30 plus 30, 60 equal to 120. Okay, volt ampere for each meter square. Okay, so what is the next step? So we have the volt ampere, total volt ampere for each meter square. We can take this value and multiply by area of the building. Okay, so we multiply by the area of the building to convert this 120 volt ampere per meter square into volt ampere. So as an example, we need 120 volt ampere per meter square. So as an example, if we have 100 meter square as an area, then we will multiply both of them, 100 multiplied by 120 volt ampere per meter square. Then we will have 12 kilovolt ampere for this bank, because 120 multiplied by 100, it will give us 12,000, okay, volt ampere. So in order to convert from volt ampere to kilovolt ampere, we will divide by 1,000. Okay, so we will have 12 kilovolt ampere for this bank. So this is the amount of power required for this bank if the bank is one floor. Okay, now what if we have several floors? Okay, not just one floor but several floors. Then in this case we will take the 12 kilovolt ampere and multiply it by the number of floors in the building. So if it is 5 floors, then we multiply this number by 5. Okay, and of course all of this is done using Excel sheet. Now before we continue to the Excel sheet, we have to give a small note here, okay, which is, as you can see here, we have all of this. This is normal, range, okay, one value, okay, which we can get any of these by the same method here, okay, average of the value, and so on. Okay, in the basement we don't have air conditioning and so on, or garage we don't have an air conditioning, so we don't have any values here. However, you will find in office, for example, we have 40 to 70 and we have 110 to 120. What does this mean? We have two values or two ranges. The first range is for air conditioning for split type, or the air conditioning which is in each room, okay, in each room, okay. So as an example, if you have air conditioning for separately for each room, then we are going to use 40 to 70 range. However, if you have an HVAC system, then you are going to use 110 to 120. Okay, so this for air conditioning, normal air conditioning in each separately in each room, but this one is for the system or the HVAC system, okay, which supplies air conditioning or cooling for all of the building. Okay, and same all of this here. Now, as you can see in the theaters, you will find 700 to 1000, very large, because the roof itself is very high. Okay, so since the ceiling itself is really large, so we need very large cooling for the room. Okay, now in the industrial building we don't have any air conditioning like factories. Okay, so this is how to understanding the code itself. So we take the values from the code, then multiply it by the area. Now let's see how can we do this by using the Excel sheet. Now let's discuss how can we do this using the Excel sheet. So as you can see in this sheet, we have the code, NEC code, and which we have just seen inside the slides. Okay. Now we are going to use this in load estimation. So first you will find lighting loads, power loads or sockets, HVAC system or mechanical loads. Then you will find elevators or lifts, water pumps, fire pumps, medical equipment, and so on, or any other loads. You can just add them here. Okay, and you'll find here the total estimated load for the building. You will find the output here. So let's say we have an area of the building, for example, is 100 meter square. Okay, area of the building is 100 meter square, and we assume that all of the floors are similar to each other. So we will say we have 5 floors, so we can say 500 meter square. Okay, this is the area of the building and floors. So we have a building which has an area. The area of the building is 100 meter square, and we have 5 floors, so we will have 5 multiplied by 100, which is 500 meter square. So we will add the area here, 500, area here, 500. Okay. Then you are going to see what type of place you would like to have. As an example, we are going to use office. Okay, the office. So what is the volt ampere per meter square for the lighting, which is this one, lighting, this one. So I'm going to use the calculator like this, and office 35 plus 15 divided by 2 to get the average. So we are going to use an average value of 25. So I'm going to add this like this, 25. Okay, like this. So as you can see, volt ampere is 25 and the area is 500. So the Excel sheet automatically multiplies these two values by each other and obtains the volt ampere required for this load. 25 multiplied by 500 like this. 25 multiplied by 500, 12,500. 12,500. Okay. Now what about power loads? Here, as you can see, small power or sockets 15. So we will type here 15. So as you can see, 7,500, which he multiplied this one by this one, the Excel sheet. Now what about the HVAC loads or the mechanical loads? So as you can see, the HVAC here, for example, the office, you can use it as a air conditioning for each room or separate air conditioning system, or you can use an HVAC system. Let's say we have an HVAC system, it can be from 110 to 120. 110 plus 120 divided by 2, 115. So we will type here 115 as the average value. Okay, so we obtained the lighting loads, power loads, HVAC loads. Now what is the next step? We need to see the elevators. So as you can see here, we have a rule. The number and type of the elevators is usually determined by the architecture engineer, or you can just estimate it. Just an estimation. It will be from 15 to 25 kilowatt. Kilowatt. Don't forget, this is not volt ampere but kilowatt. And as you know that in order to convert from kilowatt into volt ampere, from kilowatt to volt ampere, we will divide by the power factor, right? S equal B, or the active power, divided by the power factor. So we assume that the power factor is 0.9. So first, let's see the average value, like this. 15 plus 25 divided by 2. So we will need an estimation, as an example, 20 kilowatt for each elevator. Okay, now we will convert this 20 kilowatt for each elevator into S, or volt ampere, or apparent power. So we will divide by the power factor, divided by 0.9. So as you can see, 22.222 kilovolt ampere for each elevator. Now let's assume that we have 2 elevators in this building, multiplied by 2. So this value is kilovolt ampere for each one, multiplied by 2. Okay, so we need for elevators 44.44 kilovolt ampere. Okay, now here as you can see the unit is volt ampere. So I'm going to multiply this by 1000 to convert from kilovolt into volt ampere. 44,444, 5 fours. Okay, so we can say like this, 44444. Okay, then we have water pumps, fire pumps, medical equipments. All of this, water and fire pumps are by mechanical engineer, and medical equipments, of course, you don't have any knowledge about them, so you will take them directly from the engineer itself. Okay, now the pumps here, or the water pumps, is determined by the mechanical engineer. You can also do an estimation for water pumps and fire pumps, just an estimation. Each one water pumps is 5 kilovolt ampere, and each fire pump is 15 kilovolt ampere. So let's say the water pump, we need 4 water pumps. Okay, 4 water pumps. So it will be 4 multiplied by 5, since we have for each one 5 kilovolt ampere. 4 multiplied by 5 is 20 kilovolt ampere. So it will be 20,000, like this, because here we have in volt ampere 3. Okay, what about the fire pumps? Let's see the fire pumps, 15 kilovolt ampere. Let's say we have for example 2 as an example. All of this is done by mechanical engineer, but just an estimation, you can do this. 30 kilovolt ampere, so it will be 30,000. Okay, 30,000. Okay, so after doing all of this, you will find that this is your own building area. Each load, as you can see here, in volt ampere, and this, if you need any other loads, you can add them here. Now in the end, you will find that the summation of all of this volt ampere powers will give us 171.944 kilovolt ampere. So this is a small building or a small project. Now as you can see here, you have to know that 171.944, if you use a transformer, remember that the oil transformer is loaded by 80%. So we have to use a transformer of this value, 214 kilovolt ampere. However, if you look at this table, we have transformer of 500 kilovolt ampere, 800 kilovolt ampere, 1 megavolt ampere, 1.25, 1.5, 2 megavolt, 2.5. Those are the transformer available in order to add them in the building if you need. However, as you can see, the lowest one is 500 kilovolt ampere, or 0.5 megavolt ampere. However, if you look here at the required is 214.93, and when this is loaded by 80%, you will need finally 171. Okay, so as you can see, this is really low than 500 kilovolt ampere. So what does this mean? It means we will take from low voltage, and we don't need any transformer in the building, because the kilovolt ampere, as you can see, lower than 400 kilovolt ampere. If you get back to the previous lesson, we said before that if it is less than 400 kilovolt ampere, then we don't need a transformer. If it is higher than 400 kilovolt ampere, then we need a transformer. So as you can see here, we don't need a transformer. Now as an example, we can make this area 700 like this, assuming 7 floors. Okay, 7 floors like this, 7 floors. Okay, so we will have 202, still low. Let's say okay, 1000, okay, 1000. Okay, so let's see, 250 still away. So as an example, we can make this 2000, okay, or 4000. Let's make it 4000 as an example. 4000 like this. Okay, so as you can see, we need 714 kilovolt ampere. So by using calculator, we know that our transformer loaded by 80% if it is an oil transformer. So divide this by 0.8. So the transformer required is 893.055. So the closest transformer is 1 megavolt ampere. Okay, not 800 but 1 megavolt ampere, because if we choose the 800, the transformer will be overloaded, and this will mean that the lifetime of the transformer will be decreased with time. So the better option is to use 1 megavolt ampere. After doing load estimation, you will find that this value can be a little bit higher. Instead of 714, it will be 750 or 700, this range. Okay, so by doing the load estimation, we were able to get the values for our load in the building. Okay, so by using this Excel sheet, you will know what load required or the load estimation. Now, what is the next process or the next point which we are going to do? We are going then to do the sizing for transformer room and generator sizing room. Okay, both of them. Okay, which we are going to do in the next lessons.